Now we're back to the first page of your Chapter 5 notes, and we're going to discuss the molecular geometry. So we've already talked about electron region. We count the regions. If there's 2 regions, 3, 4, 5, or 6, then we can tell if it's linear, trigonal, planar, tetrahedral, or any of these kinds of things. The next situation, though, is that as we began looking at structures, scientists realized that they were still getting consistent results across different atoms, but it seemed to matter and vary if the atom had lone pairs. So the molecular geometry is a way of us kind of being able to tweak the electron geometry when we have lone pairs. It's called valence shell electron pair repulsion. VSEPR. And what we figured out is that anytime that you had a molecule that had a lone pair, it really isn't the same thing as saying, well, it's just like a bonding electron pair and they're the same. Part of the reason is because these electrons are bound and they stay stuck in there, whereas these electrons, they can move. They can move quite a bit. They can move like all around in there. So it's not the same thing. And so we came up with a kind of like an addendum to the idea of electron geometry, but we still require everyone to be able to identify electron geometry as well as molecular geometry. My suggestion on any quiz, test, or homework is that you go through and you jump to all of the problems that perchance say that they want you to figure out the electron geometry, and then work all of those. Then go back and do the ones that want the molecular geometry. I think it's really hard for our minds, especially if you're just learning this, to switch back and forth and not accidentally make a mistake where you've named the molecular geometry with electron region or likewise. So I really recommend jumping around, doing all the electron geometries first, and then go back when it requests that you name something with molecular geometry. So the molecular geometry does not change anything if there are no lone pairs. So you'll notice in this situation, so when you have no lone pairs, the name is the same. So it's still called linear when there are no lone pairs. Again, no lone pairs, it's still called trigonal planar. No lone pairs, still called tetrahedral. No lone pairs, it's still called trigonal bipyramidal. No lone pairs, it's still called octahedral. So that part of it's easy. That part didn't change. At least we're using some of the same names. So we're going to go over here and we're going to look and see. We're going to just go ahead and copy over those names for the things that didn't have lone pairs. So let's look at the first one. Obviously that doesn't have lone pairs. So we are going to copy that over. And the next one doesn't have any lone pairs. So we're going to just copy that one's name over. This one doesn't have any lone pairs, so we can just copy that one's name over. And this one doesn't have any lone pairs, so we can just copy that one's name over. Again, the reason that we can do this is that the only reason we developed the molecular geometry was because of this valence shell electron pair repulsion. And if there are no electron pairs on the central atom, then there's no valence shell electron pair repulsion. So nothing changes in those cases. So go ahead and look through the other situations, and I'll go ahead and solve it also and share the answers. But go ahead, find all the atoms without lone pairs, and just repeat their name over from the electron to the molecular geometry.